It's about to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause this stream is about to start. Get ready wherever you are, 'cause this stream is about to start. Hello everyone and welcome. This is day 26 of Advent of Code, which is an event that has 25 days. We will be doing today days 25, also 20, 21, 22, 23, and 24, of course. We are going to do all of them in half an hour. I have my pack of peanuts, and nice. I'm not afraid to use it. And I also have my good friend David with me. Hello, David.
Hey, what's up? I am ready to rock and roll. I also have done a little bit of work or playing around on these problems, but I have no progress. But I have some things I'd like to share.
Okay, so do you want to start with previous days, or do you want to jump to day 25, which is supposed to be easy, and come back to the more difficult days?
I want to share very briefly what I've got up to on day 23, and then we can talk about it. Won't take more than 10 minutes, and then we can do day 25.
All right. So what is the best way to share what you have? Do you want to show a video?
I'll share my VS Code link.
Okay.
Cool. Can you see my VS Code?
Give me some 10 seconds.
Sure.
There, I'm in.
Okay, so part 2 V2 was a kind of hybrid approach where I was thinking about junction points. It's a half-formed idea, so I'm not going to talk about V2 too much. V3 was what we said about just recursing, then creating a cache key, and then once we have that cache key, we can, if we have the cache key, then we don't need to do anything and we can return it. Otherwise, we compute effectively 1 plus the sub answer to get our answer at any junction. So all of this code, it just amounts to, like, sometimes there's only one option. So, like, there's probably a better way of reducing this, but whatever. It's sort of, because it's like a wait. So you don't have like a wait promise.all synchronous. It's all like asynchronous, and like I wanted it to be synchronous for the visualization. So this is just the way that I did it. But basically it's the like 1 plus sub answer. This works, except the memoization doesn't work. The cache key here is based on the row and the column, but it can't just be the row and the column, because you could be approaching a cell from a different direction, so it doesn't make sense that the distance beneath it works. I can actually show you this one though. Oh, I can't show you this one. But basically, you need the previous direction because I can't show you because it's going to be like in a browser, and then I'd have to share the port and all that stuff.
Well, you
and I
could
can't
also
bother
try
to-
sharing your screen on Skype. I know it didn't work
I
in the
could-
past, but it could work now. Who knows?
That's true. But I can you see why you need the previous direction?
To be honest, no, because the way that I was thinking about this is when you get to a certain point in the maze, the question simply becomes, doesn't matter what I did in the past, if I started here, what is the shortest path?
Yeah, let's go to Excalibur in that case.
I'm here.
So the reason that you need to know the direction is, I mean, let's look at this one here, this path. So here is the start and here is the end of the maze. Now, if I do this particular, there's a cell here, for example. Now, I could have got to that cell via this way. And if I do that, then the distance, the distance to getting to the end there is going to be 0 because it's not possible because it's a loop.
Mm-hmm.
Right? Annoyingly, I can't undo. But if I came from a different direction, say this way, then it should have a distance. So you need to have an understanding of direction. That's why I had the direction.
Mm-hmm.
But then I realized I wrote this code and then it just didn't work for the real input, and I came up with this example. So specifically, let me just move this a little bit. If you do, for example, I think this one. So you could have come this way. So that's one direction. That works. Or you could have come this way. Or you could have also gone like this.
Mm-hmm.
And so previous direction, the direction that you came in is also not enough. And therefore I couldn't work out a good cache key for memorizing that cell. So that's as far as I got with that. So then what I decided instead, let me just delete all of this, is the code's really horrible for this next bit, so I didn't bother. It's not worth even looking at the code. Is I just said, okay, let's just take the junction nodes. So I'm going to take this one, and I'm going to take this one, and I'm going to take this one. Because a junction node is anything which has more than one option.
Mm-hmm.
And then I will just... Oh, no, that doesn't have... That one was wrong, sorry. Yeah, can't undo. Oh, no. Okay, there we got it. And then, yeah, this one, I suppose. And then I do a sort of basic depth first search or breadth first search, and I create a new graph, which is just the distance between each of these junction nodes. And then I try and compute the longest path using these junction nodes. And then the assumption is that, like, because there's long distances between these junction nodes, you don't have to traverse every cell, and it should speed things up and should be brute forceable. Turns out I'm probably wrong. It's been running for several hours and I still don't have an answer. So that's where I got to. But any remarks are welcome. But if you have none, then I'm happy to move on to day 25.
The only thing that I can think about is to, first of all, Great explanation of what the problem is. I get it. And it makes sense because depending on how you got to a certain point, you will be able to use different paths moving forward, which may affect your count. Now, with that in mind, the only insight that may or may not be worth something is to try to put the problem on its head. And instead of going from beginning to end, is to go from end to beginning. And the reason why that could come in handy is that you could ask the questions like this. What is the longest path between this and the end? Well, it's trivially the end. Now it's trivial. This is trivial. This is trivial. Here, it's not so easy, but you could say that, oh, the longest path is, okay, from here to the end. Fair enough. And what is the longest path from here to the end? Well, you would probably need to come up with the... Yeah, I guess the strategy that I'm working out here will avoid cycles, because you could say the longest path between this and the end is just following here, because this...
Yeah, that's true.
That's kind of not true, because you could find a way to spin in a circle and come back. So
Yeah.
maybe that's not even true. But my idea would be that you would reach here a point of a more interesting junction in which you could really have... So for instance, this I would say is an interesting junction, because here you really do have two ways to go. And then in this point, you would take the maximum. And then turning the problem on its head perhaps would be advantageous. Because at this point, you would reach this point from two different directions. And you would see, okay, I have been here before. I'll just take the maximum between the two and add that.
I feel like that's what I did implement in the code that I was showing you. Because it actually, when you look at the cache keys, you don't reuse the cache value of the distance so far, because that doesn't make sense. You can't reuse the distance so far. You're reusing the future distance. So maybe if you look at the code, you might conclude that it's similar to what you were thinking. Just one final thing I wanted to say is that we could try and use heuristics. So just like you suggested, always following the opposite way on those are going up the slope kind of things. We could try that, but also just always heading in the opposite direction to the end node. We might get to a longer path quicker than not, if we prefer those options and we sort it. So a sort of A-star kind of thing, but I don't know if that I suppose that helps if you were to try and do it and try and create a really long path. You'd always try and head away from the end, wouldn't you? Might not always work, but that's one final option.
Yeah. When you did the graph version, turning the junction nodes into a graph, did you by any chance plot this graph using GraphViz?
I didn't plot it. That's a great point. I have them here, but the code is still running. I could plot that for you, and we could run it next time. I could show it to you next time.
Yeah, because maybe there is something interesting in that graph. Maybe there is a pattern that we can uncover.
Yeah, for sure. I mean, to be fair, we did kind of plot the graph, didn't we? Because we saw the maze, and it was like, okay, this is a big maze. I'm not sure how, but maybe it would be useful to see it in GraphViz.
Maybe, maybe not. Another thing we could do is just bite the bullet and read the Wikipedia article on finding the longest distance.
We could do that.
What they say, by the way, I skimmed that article, and I thought it was very interesting. You could just take the weights and negate them, so like 3 becomes -3 and 5 becomes -5, and then run a shortest path algorithm.
Interesting.
isn't it?
How does that work? Oh, so you sort of invert the problem and make the long things short.
Yeah, and I sort of spent all of 30 seconds trying to think about why that works, and I couldn't really put my finger on it. I, of course, understand that if you negate the values and look for the shortest path, or in that case, I guess the path with the lowest number, because when you start dealing with negative numbers, it doesn't really make sense to think about distance and longest and shortest. But in any case, the path with the lowest number, of course, will be the highest number when you invert it again. So I get that part. But what I don't understand is how does that avoid the problem that I brought up like 2 or 3 days ago? The problem of like when you are doing the longest path, you sort of, by just the virtue of how the algorithm is going to work, you're going to take the right path and then you're never going to visit the left one or the down one, because then this has already become the longest path, so you just keep exploring it. And that's not the way to go. So I don't know how that solution avoids this issue.
Yeah, and I don't understand how it avoids like exploring all the paths.
The problem is not even exploring all the paths, really. It is exploring all the paths without reusing work. You can explore all the... You will have, I guess, to be sure, you will have to explore all the paths, but you only want to explore all of them at most once.
Yeah. Yeah, it's weird because you have all the information. I just feel like it's so achievable. But also, if it was that easy, then why would it be like NP complete or NP hard?
Oh,
Like you said.
and what I said about taking negation or taking the negative values for the edges and all of that only applies to directly cyclic graphs.
Oh, okay.
Which in our case it is, because we are not allowing ourselves to step on the same blocks more than once.
Yeah. Is that true? Yeah. Okay, yeah, that's true. Although the graph itself is cyclical, but the path is acyclical.
True. Yeah.
Yeah. Day 25?
Day 25.
All right.
Right.
And you're driving.
And I'm driving. Oh, look at that. We have at least 1 star for every day. Beautiful.
Do I have 1 star every day?
Huh?
Wonder if I do. I'm missing day 21.
Okay.
And 25.
All right. So day 21 you can get in the repository. We wrote that code together.
Yeah.
Day 25 is an overload. Still, somehow, without snow, you go to the last place you haven't checked. The center of Snow Island, directly below the waterfall. So that would be about there, right? Here, someone has clearly been trying to fix the problem. Scattered everywhere are hundreds of weather machines, almanacs, communication modules, hoofprints, machine parts, mirrors, lenses, and so on. Somehow, everything has been wired together into a massive snow-producing apparatus, but nothing seems to be running. You check a tiny screen on one of the communication modules, Error 2023. It doesn't say what Error 2023 means, but it does have the phone number for a support line printed on it. Hi, you've reached Weather Machines and so on, Inc. How can I help you? You explain the situation. Error 2023, you say? Why, that's a power overload error, of course. It means you have too many components plugged in. Try unplugging some components and... You explain that there are hundreds of components here and you are in a bit of a hurry. Well, let's see how bad it is. Do you see a big red reset button somewhere? It should be on its own module. If you push it, it probably won't fix anything, but it will report how overloaded things are. After a minute or two, you find the reset button. It's so big that it takes 2 hands just to get enough leverage to push it. Its screen then displays system overload. Connected components would require power equal to at least 100 stars. Wait a second. Once we finish this, we will have 50, not 100. Do I have to do a previous year? Wait, how many components did you say are plugged in? With that much equipment, you could produce snow for an entire... You disconnect the call. You have nowhere near that many stars. You need to find a way to disconnect at least half of the equipment here. But it's already Christmas. You only have time to disconnect 3 wires. Fortunately, someone left a wiring diagram, your puzzle input, that shows how the components are connected. For example, then each line shows the name of a component, a column, and then a list of other components to which the component is connected. Connections aren't directional. A, B, C, X, Y, Z, and Y, X, Y, Z. A, B, C both represent the same configuration. Each connection between 2 components is represented only once, so some components might only ever appear on the left or right side of the column. In this example, if you disconnect the wire between that and that, the wire between that and that, and the wire between that and that, you will divide the components into 2 separate disconnected groups. 9 components on one side, 6 components on the other. Multiplying the sizes of these groups together produces 54. Find the 3 wires you need to disconnect in order to divide the components into 2 separate groups. What do you get if you multiply the sizes of these 2 groups together? And this is our input.
All right. So I think this is known as a bigraph. My memory served me correctly. So I don't know. Bipartite graph, yeah.
Can I get a picture of this?
There was one on the previous page. Yeah, that picture.
So we are trying to find these wires and disconnect them.
How do we check if it's a bigraph?
Well, how to check if it's a bigraph given a bigraph is not terribly difficult, because you can start at any node and do a search and saturate and find all the nodes that are connected, and you will see that some of the nodes are not connected. So that's easy enough. But how do we find which wires to disconnect to form a bigraph? I guess is a more...
Is that the question they asked? Which ones to disconnect?
That's how I understand it. So this is going to form a graph that is connected.
Yeah.
And we need to find 3 wires, 3 connections, 2 edges that can be removed such that this will become a bigraph.
Okay. I mean, we could probably brute force the wires. We can have an easy way of checking graph or not.
Okay. We can start with that. So now I am going out of your live share into one of my own. And I'm starting day 25. And even in the big input,
Sorry about that. I was just had to attend something.
are you good to continue?
Yeah, I'm good to continue now.
Okay,
Sorry
okay,
about
okay. No worries. No worries. So now we have our input. Let's form our graph, which we are going to represent with a map, an adjacency list. And is this the best representation?
Sorry, did you decide on a general strategy?
Well, first of all, I'm just dealing with the parsing, and I'm going to try the brute force approach that you mentioned.
By the way, if you want to have some fun, we could always use the viz.js and just see the bipartite graphs.
Yeah, let's do that. I want to do that. And that works in the browser, right?
Yeah, it works in the browser, yeah. I mean, I would recommend using Parcel because it's very painless to set up. But yeah.
Okay. As someone who has never used Parcel, I don't know how to do it, but we can look into that in a moment. But first, let's just decide how we are going to represent this graph, because usually we use an adjacency list, which is good for directed graphs, but since this one is not directed, I think maybe something else. Yeah, I think I'm gonna use just a list, and I'm gonna do it like this. Input, trim, split on the new line.
New line dot map.
This time I'm not gonna map. I'm gonna just yeah.
I thought we were gonna.
I know.
Have a chorus. Okay.
So I'm going to split this into from and to, and our twos, multiple, plural. Splitting on the column.
Column space, probably. Did you share, by the way? Did you share?
It's on Skype, the link. If you cannot get in, then
got it.
let me know.
Sorry, my bad.
No worries. No worries. So I'm going to get my twos and trim and split on the space. And
do you want to do that?
It doesn't matter because I put a trim here. You may put it or you may leave it as you wish.
Yeah, I see the trim. Yeah, got it.
And then I'm going to get my graph and push my from into. Okay, does that look right? It does. So now, do you want to take do you want to take this in the direction of let's try and visualize this, or do you want to take this in the direction of like let's implement the brute force approach?
I think more efficient if we can implement the brute force approach.
Okay.
I have a little bit of analysis paralysis because I kind of want to do both, but yeah, I don't know how you're going to implement the brute force approach yet. While I understand you can just remove the connections one by one and see what happens, I don't fully know.
Well, here's how I'm going to do it. For let's say connection 1, or I'll call this the edge 1 index. It starts at 0. It goes up to the graph length and it goes up. And I guess when I finish writing this for loop, it will become apparent why I'm representing the graph in the way that I am.
Yeah. Because isn't it like not just a from to, it's like the inverse also exists. But you can always just sort them to check, I suppose. Are they unique?
What?
Are all of these edges unique?
They should be according to the problem statement.
Got it. Okay.
So now I will define what is called the bi-graph candidate, which will be my graph, and I will slice and then from edge 1 to 2, and from edge 2 to 3. And now let's make sure that we actually take elements out of the thing. So I will want to +1.
Why less than or equal to the graph length?
Yeah, that's wrong.
Okay.
And just make sure if I have a list and I slice on like after the end and way after the end, I get an empty list. That's...
Oh. Well, no, but you started slicing after it as well.
Yeah, but that's my intent.
Yeah, okay.
Just wanted to make sure. If I go over on the right-hand side, then that's fine.
Yeah.
But just making sure that if I go over even on the left-hand side, that's also fine. So these people, in fact, may not even be removing stuff at all. But by the time that this becomes a problem, this will not become a problem. This is wrong, but it will not become a problem, because if we don't slice enough, we will have too many edges, and that will make the graph even less bi-graph. So whatever, let's just move on.
You could, but couldn't you slice too many here?
What?
Like, edge index is going to go all the way to the end, isn't it?
Yeah.
So you could slice everything in the middle. So you could just have one edge, and you might have one edge, and therefore it is a bipartite graph. You know what I mean? Like, you could end up
No.
in a situation.
No, wait a second. No, this takes everything from the beginning up to the first index.
Yeah, so say edge index is 1. And then edge 2 index is like, you know, n minus 1. Then yeah, no, you will slice at maximum 1. Yeah, okay, fine.
Okay.
Okay.
So now we need to check if the graph is a bi-graph. So I will also, besides having the graph, in fact I will call this.
No, sorry, I do want to check this. So in this scenario, you'll only end up with a bi-graph candidate of length 1.
No. I'm slicing
So this-
from 0 up to 1. That will give me something. Then I'm slicing from 2 up to n minus 1. I will get a bunch of stuff in there.
Yeah. Sorry, my bad. Okay.
Okay?
So, yeah.
Okay. So I want to rename this from graph to like edges. And I will also want to have the nodes. Yeah, that. And then I just want to make sure that I got the nodes right. Keep doing that.
No, these all need to be lets, I guess.
All right. I got the nodes.
Cool.
And I suppose they're all there. So now, for each candidate, I will seeing nodes, and I will just randomly take one of the nodes. So which could be 0 arbitrarily, so not randomly. I will arbitrarily get one of the nodes. I'll always get the node in the beginning. Then
did you need to spread nodes? Did you need to spread the nodes?
Yeah,
there?
because I have a set, and I want a set because I don't want to repeat when I do
Got
all
it.
this pushing.
I see.
I could also have flattened and created it from the edges, but well, whatever. So now I will have a work list. That starts with this. And while the work list has elements, I will get my node. I will get my work list. I'll pop from it. If my node is in the seeing nodes, then continue. Otherwise, I will find the nodes that are connected to this. So I will call this the connected nodes. And they are going to be my edges. And I'm going to flat map. And I will edge. And if my edge at 0 is equal to my node, this node, then return a list of the edge 1. Otherwise, if my edge 1 is equal to my node, return a list with the edge 0. Otherwise, return an empty list. Finally, create a new set out of that. Then,
I don't know why you're working with lists like that, though.
huh?
Why are you returning arrays and flat mapping? Why not map?
Because then I can get rid of edges that are not involving my node.
Oh, that's nice.
Thanks. Now I am checking. These are my connected nodes. I guess I should be just pushing into the scene nodes, right?
Yeah.
Oh, and also into my work list. Yeah. So the flat map was nice, but it's kind of unnecessary because I can do it in some other way. I will get one of these guys. I think I'm going to put my scene nodes here. And I'll add to my work list. There. I feel like I want to read over this because I'm not so sure I wrote it right. Well, for one thing, I am going over the graph and not the by graph candidate, which is wrong. Oh, and I'm now calling it edges, so guess I'm gonna call this edges candidate. Edges by graph candidate. By graph edges candidate. By graph candidate edges.
Yeah, I like that best.
Okay. So my by graph candidate edges is that. And when I'm looking at the edges, I should be looking at my by graph candidate edges. And I think that does it.
Well, you will be able to iterate through from one node to all of the nodes. But how does that tell you whether it's a bigraph or not?
Well, I haven't finished. So if my nodes size is equal to my scene nodes size, then that's not a bigraph because I have been able to find every node. But if they are different, then I will console log my edges
But
at.
even in a bigraph, you can get to all the nodes even though you're not. You see what I mean? Isn't it about the nodes that you're directly connected to? Because here you're adding all of the connections of your connections.
No, wait a second. Then I am misunderstanding what a bigraph even is.
Well, maybe I'm misunderstanding the algorithm, but...
Okay, let's go over what I am thinking and see if it makes sense at all. My idea is that so maybe this is not a bigraph at all. The problem is not describing a bigraph at all, because the way that I'm thinking is that these nodes can be connected between themselves, and these nodes can be connected between themselves, but these nodes are not connected to those. And vice versa. So I guess this is not a bigraph at all.
Yeah, okay, so maybe we remove bigraph from our code. Misled us a little bit there. Because then that makes sense. Like if they are too isolated, there's probably a term for that too.
I'll call this like a disconnected graph, for the lack of a fancy word for it. But does that make sense?
Yeah, 100%.
Okay, so we got ourselves an n squared algorithm, where the n is the number of edges, which is not ideal, but it's not terrible. And
isn't it n cubed?
Yeah, I said squared, didn't I? It's n cubed. Thanks. So it's not terrible. It's not awful. It's not exponential. So I'm popping from the work list. I'm checking the scene nodes, adding to them, then going over the edges, finding a connected node, putting them on the work list.
Wait, hold on. Isn't exponential anything which is just growing at a factor? Isn't squared even exponential?
O of n cubed is polynomial. O of 2 to the n or 3 to the n, to make the comparison even more to the point, this is an exponential.
Yes. Okay. Sorry. Yeah.
All right. So if on top of all this it works even better, well, we got ourselves some 3 edges that we could remove to form a bigraph. And are these the edges that they proposed? They are. If we disconnect the wire between age f and x. Age f and x. Yeah, no, that's not one of the edges that we got. Well, wait a second.
Is there only one solution though? Do you break after? Do you break after you find a solution?
I suppose yes. Because if there are different solutions, then the number of components on each of this, let's say, subgraphs or disconnected groups, there would be different numbers here, and their answer wouldn't be unique.
Yeah.
So we were not, in fact, capable of finding. And given that this is like the first couple nodes, I'm pretty sure that our algorithm is just wrong.
Okay.
It's not visiting every node that it should. Also, I probably don't want to just print this. I will also print console log of scene node size times that, because that will give me the final answer that we need to produce, which is not in fact 14. And 14 is probably the number of elements here. Not even that. There are 15 elements. So let's work.
Can we see the edges, the disconnected graph candidate edges?
They are these.
In the first iteration. No, but aren't those the edges that you removed that you're displaying?
Oh, and I'm doing it wrong, right? No, I'm doing it right. Okay, can you say that again, please?
Can you print disconnected graph candidate edges on the first iteration?
Do you mean to print this when
Yeah.
we are here,
Oh yeah, just like at the beginning.
right here.
Because I think it's exiting on the first
It
iteration,
is.
right? So yeah, just print that. See what it is on the first
Ah,
iteration.
okay, I see what you mean. And also, I think it would be fun to compare it to the edges.
No edges.
Mm,
Is it because we start at 0? We need to start at 1. But also,
come on, what?
yeah.
Well, let's take it from even more the top. Jeez, Louise. All right, people. What does it mean to slice with an edge index of 0 and edge 1 of 1? I'm saying the numbers all wrong. At least I'm typing them right. This is going to be the first iteration. So
Yeah.
we are supposed to be dropping the first 3 edges. And we know that we are not.
Doesn't make sense.
Yeah. Okay, we can reproduce the error in a simple problem. Simple program. So this is fine.
Yeah.
Oh, we are missing one. That's what's up.
Ah. Good catch. I was not seeing it.
Nah, it's gonna complain. But whatever. Okay.
That's it.
Yeah, we are removing 3 elements. So we have 1, 2, 3, 4 segments. And we also want a +1 there.
Mm-hmm.
All right, people, we are back on track. Okay, we printed a bunch of stuff, but we got our 54 in the
54.
end. Excellent.
Very nice. Very minor off +1 issue, but other than that, we're good.
We are. So, how did you spend your Christmas, David?
I spent it eating a lot of food, and we went to Richmond Park as a family, went for a walk, took some photos, and didn't do very much exercise. And that's about it.
Well, over here, we had a shepherd's pie that was fantastic.
Did you really?
Yeah.
Ah,
It was made out of chickpeas and lentils, and today we had a
yeah.
variation on that using sweet potatoes as well. Yeah.
Is everyone vegetarian?
Well, I am vegan, and then there was one person in Christmas that was vegetarian. I guess 2 people who are vegetarian, and then 1 flexitarian, and then 2
What's
omnivores.
flexitarian?
Huh?
What's flexitarian?
Well, thanks for asking. It is someone who is, for most of the time, eating mostly vegetarian or
Right.
even mostly vegan, but who is flexible and who may eat meat sometimes.
Oh, so somebody who's only vegetarian to flex. as a flex. Got it. Got it. Okay. This is taking a long time, I guess.
Any plans for the new year? How can we make this faster?
Yeah. I guess not making it cubic.
Are we talking about a huge number here? Let's
Should
check.
we visualize it?
That could be cool. Even if we get
Alright.
the right answer, it could be cool. But I do want to know how many edges we have in the real deal. And what is this number cubed? Okay, that's a respectable number. It's in the 40 billion. But I have left my computer running one of the problems overnight, and it did more than 40 billion. So I suppose the brute force is going to finish in reasonable time, and I will leave it running unless I goof up something over the course of this stream. But let's indulge the idea of visualizing, and let's perhaps consider how we can make this faster as well. But yeah, do you want to start with the visualization?
Yeah, let's do it. I was going to say parcel, but the only reason I needed parcel was because I was writing it in TypeScript. But you could just well, I'm not sure how easy it is to import this module using script.js. Just like a script tag. But if you prefer to do it that way, that seems pretty simple. Let's have a look. Viz.js is the one.
Okay, I'm going to create a file called 25.html. I will... Wait a second. No, I have a better idea.
Okay.
I will call a file, create a file called 25 visualization. I'm going to grab some of this code. Eesh. That's no good.
You trim it though.
Ah, okay. And I will console log or even I'll start modifying this code right in there, right in place. I
think you'll need an adjacency list for this. I'm not sure.
There. Okay, that produces GraphViz output. Is there a semicolon at the end of the line?
Oh, nice.
Indeed, there is. And now pipe into pb copy and paste there. And syntax error in line 1? No way. Why would you say that? No, really, why? Do I have to paste here? Is this online thing not going to be fast enough to compute such a big graph? Yeah.
Mm.
What if the graph was smaller? Okay. And also I made this a directed graph, so I should be using this instead, right? Graph this undirected graph. I forget graph this syntax. Okay, it's just 2 dashes. I still see a syntax error.
Are there some examples? Like, just, I don't know, just look at some examples maybe?
Huh, then it works. Oh, because it was graph and the other was a dgraph, which is directed graph.
Ah.
Doesn't get simpler than this, right?
Right.
Right. So does it get simpler than this by not naming the graph? Yeah. Okay, so we learned that this will not finish because it's trying to do it
However,
in the browser and stuff and all of that.
but there will be an online, there'll be a JavaScript one, I'm sure.
I can also brew install GraphViz.
Go to viz-js.com. And try pasting it in here.
Okay. That works.
Let's have a look.
That's these three. Thanks, Viz, GraphViz layout engine.
Yeah.
Oh, I was trying to scroll to the side and I went to the previous page. Okay, so all we gotta do is fish the 3 edges here.
Yeah. Well, I can see one of them. It starts with PK.
Huh?
If you zoom in, you can see one node that it connects to.
No way, can you?
Go to the right.
Oh.
Yeah.
Yeah.
GSK.
GSK. Okay. And GSK connects to 4 things, but from these 4 things, we are interested in... Wow, this is a ball of wires. I can't believe that we are doing this. No, it's just impossible. Look at this. Here it goes like...
Yeah, who knows?
Yeah, what I wish I could have was some way of like clicking on one of the dots and interacting with it.
Yeah, that might be an attribute in if you look at the GraphViz documentation, like an attribute for like labeling the edges or tapping the edges or something.
But that's not what... Ah, you would label the edges with numbers and then look at the number that comes up here.
Yeah, yeah. Or you could label it with the actual what it is. But then hopefully the label's in the right place. But yeah. What's the documentation for labeling an edge? Yeah.
No.
Yeah, that'll be it. Okay, so it just goes afterwards, I guess. Well, I think it'll be like title equals or something like that. Label equals. Yeah, it's label equals. Okay. Yeah, so give that a go. If you put it in quotes. syntax error, so. All right. Very efficient. Hopefully it will label it right in the middle.
Yeah. Do you know of any visualization tool that will do what I want, which is to like make the graph interactive? Because it should be doable with like GraphVis for like the engine, and then something like whatchamacallit,
We could you can add class names to things, so we could just inspect. This is actually an SVG on the right, so we could just inspect element and then. Okay, might need to zoom out a bit to. All right, hopefully it's just bang in the middle. No.
Well,
but try inspecting element.
I suppose that this is that. And this is that.
So.
This is our GSK. We have seen it.
Yeah, but.
Oh, shucks. Okay, so what you're telling me is that I should look at this. What the hell? It's just one big image. It's a blob.
Try changing layout engine. Oh no, no, it's an SVG image. But this one is like. I guess they compile the SVG image separately. I think it's like maybe like I don't know how they've done it, but it doesn't look like they've included all the SVG elements. They've like maybe done it on a worker and then like copied it across and like populated a cache, or I don't know. It's annoying because when I did it, you could inspect the elements. You can change like, yeah.
Come on, people. All I want to see is click on an edge and see what are the dots that are connected to it. It shouldn't be that hard. Why are you making this to me?
I guess you could position the labels maybe in an absolute position so that the X is always in the center of the image.
What is the X?
No, I'm just trying to think if there's, without making it interactive, if there's a quick hack that we could do. I mean, definitely if we, installed Viz.js in our MJS file, and then we rendered the SVG ourselves.
Is there a way to download this image?
Change the output format as, yeah, if you can download that.
I want to download it in which version, in which format, but this Viz.js doesn't even, this specific implementation we are looking at doesn't even give me a way of downloading anything.
It will if you keep the network tab open. Won't it request this image if it's URL, and then you'll be able to follow that? So you have to change it from JDK to some other node, and then change it again. Like just change the node so it stays valid, but yeah.
How the heck does this thing work? Think of a roundabout way of solving the problem, right? But it's day 25, people. Let's be creative. Yeah, this thing is not rendering in the cloud. This thing is rendering on my machine.
Yeah. But I think it could be going to it. Keep it open. Keep it open. Keep it open. Because like it's still doing the work. It's still building the image. So let's wait until it's built the image locally, and then it should make a request. I reckon. Even if I don't think it'll be a request to the server, but
it's funny how the labels really add to the computation time, right? Okay.
There you go. That blob. Can we? No, I don't think. I think just click on it and you can get the response. Get the response out. Yeah, that's what we need. So put that in an HTML file.
I want to make sure that I don't open this in Inkscape.
Got it. Okay, now we should be able to inspect.
Okay. I sure hope that they put the label somewhere sane. Or that this drawing algorithm works in a sane manner. Aha!
Make it like blue to verify it's the right. You tap the right one. The stroke of the path.
Yeah, there is no easy way of verifying that, but
yeah, you can just change the stroke there.
Ah,
great. So copy that. Put that in your clipboard.
I love this. I love everything about this. To get your star, you also have to go through all of that.
Oh no.
Did I miss one? No, it's gonna be these two. Okay, I got this. I got this.
How are you sure that's the right one?
When I put my cursor on top, the blue rectangle kind of started in JSK, so it looks correct, but...
Yeah. Got it. Yeah, I mean, it does say GSK, so... Okay, brilliant. And then we got one more, I guess. Rebecca Purple.
You know the story, right?
Knowledge. No.
No?
No.
Oh, it's actually it's sad and cute. One of the people who worked in CSS, I mean, like in the early days of CSS when the colors were still being defined, I think they lost their daughter who was named Rebecca. So they included Rebecca Purple as one of the colors in CSS forever and ever.
Oh.
All right, so these are the three edges, people. Now we have to write a little program that will compute the sizes and multiply them. So now this is going to be like brute force.
I guess we could just manipulate your existing.
There are several ways of going about this. But
I guess we could just sort it so that like the first three are the edges that we want. And then we don't need to modify the program.
I see what you mean. I'm thinking of just letting these indices be the right indices.
Okay.
And
You need to get them in order.
does it even matter?
I think it does, because aren't you like basing it on the fact that like one is before the other? Could be wrong. Because if one is like after the other, then it will have like some weird consequences, I would have thought.
When doing this, right?
Yeah. But you can change that, I suppose.
No. I guess I would just do a bigger modification on the program. So I'll do this. You can see the brain thinking here, right? You can see all the backs and forths.
Yeah.
There, that.
Did you? Interesting. Yeah.
Woohoo!
Wow.
Well, I want to thank the Graphis arrangement engine. I want to thank David for coming up with the visualizations. And I want to thank the Academy for coming up with Advent of Code.
Wow.
And that's how you do it, folks. Easy peasy.
Wow. I guess looking at it,
Yes, looking at it.
I mean, looking at the graph, it feels like it should be possible to compute this. I don't know, relatively easily.
Well, we could build the graph using GraphViz. Then we could look at we could come up with like a clusterization image visualization thing, because there is a very discernible cluster. Or we can even go with the heuristic of just splitting the image in the middle. Then, how about that? We split the image in the middle. Then we do some sort of image visualization thing to get all the nodes back using some like character recognition thing. Or just count the number of circles.
Oh my god.
Or, of course, we can think about how we would solve this problem for real without brute force.
Yeah.
How would you solve this problem for real without using brute force?
I think for that you need to be able to test whether one element is like bridging two clusters or not, one edge. My immediate thought is like you don't need to. You instead don't follow every edge like in a loop, like a breadth first search, like recursive thing. Instead, you just take each edge and then like form it into a cluster. If you see what I mean.
Can you elaborate on that, please?
So like you just you start with like many clusters. And then you should end up with one massive cluster. In the end.
What I am thinking about is, what if we, for each node, collected the degrees of separation between each and every other node? Then sort these lists by such that higher degrees of separation, let's say, come at the end. So this way you are finding a node and not only its immediate connections, but also its neighborhood, let's call it. And everyone on its neighborhood will be in the beginning of this sorted list, and everyone in that other neighborhood will be further down the list, because they have to go through all the hops to find the guy who knows the connection with the other cluster, and then from the other cluster all the way to the node in particular, right? So it stands to reason that the degrees of separation between this node and that is lower than the degrees of separation between this node and that. And that's kind of like starting in the right direction. You could at least with that put some order to the brute force search.
Yeah.
Which would perhaps find a solution faster. Do you want to take a look at part 2? I think that day 2 doesn't have a part 2. It's just like if you have collected all the stars, then you're good. And then we can look at the Reddit, if that's the case. But let's see. Part 2. You climb over weather machines under giant springs and narrowly avoid a pile of pipes as you find and disconnect the 3 wires. A moment after you disconnect the last wire, the big red reset button module makes a small ding noise. System overload. Resolved. Great reading, Leandro. System overload resolved. Power required is now 50 stars. Out of the corner of your eye, you notice goggles and a loose-fitting hard hat peeking at you from behind an ultra-crucible. Okay. You think you see a faint glow, but before you can investigate, you hear another small ding. Power required is now 49 stars. Please supply the necessary stars and push the button to restart the system. You don't have enough stars to restart the system, though. You need 5 more. Aha. So yes, it's just a case of solving the problems that we still have remaining, and day 25 will solve itself. So do you want to take a look at the subreddits to see ideas, or do you want to wait and think of smarter ideas?
Degrees of freedom I like a lot. Well, not degrees of freedom, degrees of separation. Yeah. Let's look at subreddit.
Okay.
I bet some people did it like we did it.
I bet some people are going to be like, oh yeah, of course, you just have to use the fancy pants theorem. But wait a second. Okay. No, I was going to say that this problem was relatively hard because the first person took 14 minutes. But no, the whole leaderboard was filled in 14 minutes.
Wow.
Okay, Python. For a final finish of 4th on the global leaderboard, at first I missed the remove 3 edges a bit and thought it was just looking to find this. Okay.
Minimum cut.
Huh?
Minimum cut.
Lucky for me, the documentation page for minimum cut is quite good, so it went pretty quickly. About network X?
Is that some graph library for Python? So they just use like min cut or something to...
So they're saying they use that library.
Yeah.
And compute the value and the node partition. That's the name, a partition. Not a bigraph, but partitions.
Mm-hmm. Yeah.
And then there is this ST cut. What would be that? The S is the source node and T is the sink node. Use the max flow min cut theorem. The capacity of a minimum capacity cut is equal to the flow value of the maximum flow. I am missing some jargon.
I always found the water flowing graph algorithms really difficult to understand. Or just, it's like graph, it's just like they have all these like pipes, connected pipes, and then there's like water flowing through the pipes, and then you have all of these things about theorems about that kind of thing.
Yeah, so they use the library.
Yeah.
Okay. Devise the simple ad hoc algorithm. We are looking to split the graph into 2 components with exactly 3 edges crossing the component boundaries. We define one component as the set of nodes S. The other component is the whole graph minus S. We start with S is equal to the whole graph, that is all nodes in one component and the other component is empty. For each node in S, we count how many of its neighbors are in the other component. Nodes with many external neighbors clearly do not belong in our component, so we iteratively remove them from S. What does it mean to be an external neighbors? They are implicitly added to the other component. We repeat this until the nodes in our component have exactly 3 external neighbors, and we are done.
Used iGraph, so another graph library.
Let's see if the code helps. Start with S. Count is what is V? Probably one of the nodes.
Yeah. Well, S is the set of nodes, isn't it? And then the graph is the actual graph, and you're getting a particular, I guess, subtree. I don't know.
I don't get it.
What GP is.
Just 3 lines. These people. Okay. Any solution that we can understand? Well, I see lots of folks just render the graph and use their puny human eyes. That's me. I have human eyes to figure out where to make the cuts and used some algorithm that I didn't know, but have made a note to look up later. I instead decided to do a dumb thing. I figured that the graph had to have some sort of 3-add bridge in order to be solvable. So, build the graph, pick 300 random node pairs. For each of these node pairs, figure out the path from point A to B. Keep track of the nodes you see most often in all of your paths. Take the 6 most popular nodes and cut them. Use the counts since each side of the edge should match up, and hope you don't get unlucky with duplicate counts. 5-step A, optional but happened to me. Fight with the borrow checker until Rust spits out the binary. Okay. Okay, so their idea was essentially this idea of the neighbors, the neighbor counts, but they did it statistically, which is very interesting to me.
Yeah. Dijkstra, hold on. Dijkstra from each node.
Okay, when I see that. Dijkstra starting from each node, and Dijkstra, not A star this time. Get all the shortest paths from each node to all others. Count each time you see an edge on the shortest path. The top 3 must-seen edges are the ones that must be cut.
Yeah.
Okay, it's kind of what I said.
Yeah.
Right?
It's very similar to what that guy said too. Yeah. Yeah, nice.
Monte Carlo, so yeah, it's going to be probabilistic, and it's probably going to do that idea again. But let's see. We'll choose 2 random nodes, get some path between them, and then count the number of times you see an edge in the path. Cool. Using the the statistical approach is nice.
Yeah. Network X. What are people just using graph libraries?
Yeah. That's for people who want to be fast, not for people who want to be cool.
Graphiz.
What?
Somebody using Graphiz.
Yeah. Again. Yeah, then BFS from any node, excluding those so that you can count. That's what we did. Yeah, now they're using this lingo of cuts, which I think is just like removing edges, right?
Yeah.
And then they are using this flow, which I'm not sure I understand.
Yeah, that's what I was talking about, like flow and cuts algorithms. That's the
So graph, flow, and cut.
yeah. There's some max flows, minimum cuts. Yeah, this stuff. Max flow, minimum cut theorem. There you go.
Well,
Yeah, this one never.
this is gonna go into my for 2024 list.
There we go.
A cool linear algebra trick. Is there one with VimScript? Nah.
You have to search the comments. You can't search like that. It doesn't render. It's like all virtualized. You have to scroll to the top to search the comments.
Huh.
Scroll down a bit. There.
Huh.
Just try Vim. Guess not.
You can read up on some of the weird math graph theory here. Partitioning a graph using the Fiedler vector. Wow. Look at that, there are articulation points. There are Fiedler vectors. Oh, wow. There is algebraic connectivity. Okay, I'll take a look later. The basic idea is that you can drop the graph vertices / nodes onto a number line based on their connectivity. And 0, 0 is where the partition is. You could double check by looking at edges that connect nodes that are on opposite sides of 0, 0. These are the 3 edges you would actually cut. And there is some wizardry. And there are some eigenvectors.
Oh.
Wow.
I vaguely remember eigenvector. I can't remember what it is.
These people are smart.
There's some smart people wasting their time with Advent of Code.
Hello, everyone. Hello, Amarth Dai, Juan Carlos, Nodbuzz1, and Bo. Thanks for joining us as we solve day 25 of Advent for Code. And I suppose tomorrow we meet to continue working on the days that we haven't finished, right?
Yes.
Okay. So that was a fun day 25. I love our roundabout solution.
Yeah.
I left the program running until the end of the stream. It did not terminate, but I'll leave it running overnight. Why not? Electricity is not so expensive. And
you're not paying the bills where you are, to be fair.
Huh?
You're not paying the bills where you are, to be fair.
Oh yeah, that too. So even more reason. Yeah, so I'll see you again tomorrow. We have not decided on the time, but I'll see you tomorrow. And thank you to everyone who was on the chat. Thank you very much, David, for coming up with this idea. I love it. I hope that we can finish before 2024.
Hopefully.
And yeah, have a good one, everyone. Bye.
Have a good one. See you tomorrow. Bye-bye.
Thank you for watching the stream. You know how great it has been. Or maybe it sucked, and I am glad that you stuck with me. And soon we'll all be back together for some more coding or talking or chilling. The next time I'll be streaming.